Welcome, Wildcats. This is the Unit 3 review for Chemistry, Millard West High School. To complete the following diagram, I'm going to use a series of pages for each separate element, largely just due to the space concerns. The reason why we do electron configurations deals with our ability to model or to demonstrate where electrons exist in atoms. The first number, which is known as the principal quantum number, is basically it tells you do the electrons exist in the first, second, third, fourth, fifth, sixth, or seventh energy level. The letter that follows is what is known as the sublevel. It's basically it's going to tell you the orientation or the shape in which these electrons travel. Do they travel spherically, planar, in the directive plane, or the finite plane? And then finally, it'll tell you, the second number is going to tell you how many are traveling in that specific energy level and shape. Okay, the first element on the table is phosphorus. I generally like to start with the electron configuration. So the second column, that's the 1s2, 2s2 business, then go back and do the orbital filling diagram. So I use the electron configuration as my guide, and then I do the lines and the arrows for the orbital filling. Then I'll go back and identify the number of valence and draw the electron dot or the Lewis dot diagram. So phosphorus, using a periodic table, I notice the electron configuration for phosphorus is 1s2, 2s2, 2p6, 3s2, and 3p is the third one over. And so what would an orbital filling diagram look like for this? Well, every time you have an s, you need one line. There's the 1s2. Here's the second energy level, 2s2. Every time you have a p, you need three lines, px, py, and pz. Under the middle line, 2p. They half fill with the electrons of like spin before they pair up. There's 2p6, 3s2, and then three more for the 3p, and they should go 1, 2, 3 all up. So there is the orbital filling diagram for phosphorus. Identifying the number of valence electrons. In looking at this, valence means the outermost energy level. Notice the outermost energy level is the third energy level. You have two that are traveling spherically, three that are traveling planar. I don't care that they're traveling in different shapes. The only thing I'm really concerned about is that they are indeed the valence, the ones in the outermost energy level. So 3 and 2, it has 5 valence electrons. And so to draw a Lewis diagram for phosphorus, element symbol, first 2 I'm going to place there, 1, 2, and then 3, 4, 5. There's phosphorus. For neon, I'm going to start with the electron configuration once again. 1s2, 2s2, 2p6. Orbital filling diagram, 1s, there's the 2, 2s, 2, 2p, 1, 2, 3, 4, 5, 6. And so you will notice that neon has 8 valence electrons. It has its perfect octet, the second energy level. There are 6 traveling planar, 2 traveling spherical. And so the symbol for neon, 1, 2, 3, 4, 5, 6, 7, 8. Beryllium's electron configuration, 1s2, 2s2. So an orbital filling diagram for beryllium would look like this. There's your 1s2, 2s2. Number of valence electrons, it only has 2, those 2 traveling in the second energy level spherically. So 2 valence electrons. And so Lewis dot diagram for beryllium looks like this. The electron configuration for fluorine is as follows: 1s2, 2s2, 2p, it's the fifth one over, so an orbital filling would look like this: 1s2, 2s2, then 3 for the p, 2p, and you go 1, 2, 3, 4, 5. And so the total number of valence for fluorine, notice you have 5 traveling planar and 2 traveling spherical in the second energy level, so therefore you have a total of 7 valence. The symbol for fluorine, there's the first 2, 3, 4, 5, 6, 7. The electron configuration for potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So the orbital filling diagram: 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, and 3s2, 3p, 1, 2, 3, 4, 5, 6, and then finally 4s1. The total number of valence for potassium, it only has one valence electron, and so its symbol is that. As you can see by the following diagram, wavelength and frequency are inversely related. Wavelength is just simply what it sounds like, the length of the wave, the distance between a crest and a crest, or a trough and a trough. So the length of the wave, you'll notice that the shorter the wavelength, the greater the frequency. Because all of these electromagnetic waves travel at the same speed, the speed of light, frequency is just a measure of how many cycles, so how many times the wave oscillates back and forth per second. And so if you were standing, at a point over here, and you were to count like how many waves pass by in a given amount of time, this would have 4 waves that would pass, and the same time this one would only have 2. And so this one, much longer wavelength, but a lower frequency. Frequency, wavelength, inverse proportion. Atoms emit different colors of light when their electrons absorb energy from some external source. It could be from high voltage electricity. It could be from heat generated from like a Bunsen burner. It could even be from light. So anyway, what happens is that you have some external source of energy striking this electron, and what happens is that it goes from its ground state, its lowest energy state, and it's going to jump up to what is known as an excited state. Well, I like to use the analogy of taking a football. A football's there and it's at rest. You pick it up and you add some energy to it with your foot. You kick it up in the air. It goes up in energy, but what goes up must come back down. As the football comes back down, it releases that energy until it comes back to rest on the ground. The same thing is happening with this electron. As it's absorbing energy, it's going to go up in energy to an excited state, but then it's going to fall back down to its ground state, where it wants to be close to the nucleus. As it falls back down, it releases energy, and that energy is going to be in the form of visible light. And so, if it only falls down one energy level, it might give off a specific wavelength, but if it falls down, it can fall down multiple. Say the electron were maybe out here in its excited state. And so it went up this way, and as it fell down this step, maybe it gave off a certain wavelength. And as it fell down the second energy level, it gave off a different wavelength. What happens is that as we observe these different wavelengths of energy being released, these specific quanta of energy, our brain takes them and assembles them into one color, even though they may be, several different wavelengths. You can observe this by looking at light emitted from atoms through a spectrometer, and that has a little prism in it that separates the different wavelengths of light. The equation that relates wavelength and frequency of light is as follows. C, which is a constant speed of light, equals lambda, which is wavelength, times nu, which is frequency. And so all I need to do is fill in what I know and solve for what I don't. Speed of light, being a constant, is 3.0 times 10 to the 8th, and the unit meters per second. In this case, I do know the wavelength, 5.50 times 10 to the negative 8th meters. And I do not know the frequency. That's what I'm solving for. And so to solve this formula, I need to get x by itself. I'm going to divide both sides by 5.50 times 10 to the negative 8th meters. I will do the same over here. 5.50 times 10 to the negative 8th meters. This whole side cancels out. Notice the meters are going to cancel. So when I enter my calculator, I hit 3.0 EE8 divided by 5.50 EE negative 8. And my calculator gives me the following result. 5.45 times 10 to the 15th, and the unit is per second, or sometimes known as hertz. Valence electrons are simply the electrons found in the outermost energy level of an atom.